Greetings, chemists. This video, we're going to be looking at acids and bases, which you may or may not be familiar with already. But let's start talking about what we call acids and what we call bases. The original term for an acid actually is I don't know if it's the original term, but a term from long ago for acids that comes out of Germany was literally called Sauerstoff, which literally means sour stuff because acids have like a sour taste to them. If you've ever had anything with vinegar in it, vinegar is a very common acid in cooking, like a vinaigrette is made with vinegar. It tastes very sour and tangy, and people like that. So chances are, if you are eating a sour candy or a sour meal or something flavored with sour, that's probably coming from something acidic. Bases tend to be bitter. So one way we recognize them is because your tongue has a very good taste receptor on it, very good chemical receptor, and can tell them apart. So if we're making a list here, acids tend to be sour. Bases tend to be bitter. What else happens? One thing we notice with common acids is that when you put them in water, they conduct electricity in water. You may have heard of battery acid. Inside of, if you were to open up a car battery, inside of a car battery is an awful lot of sulfuric acid, which is a very strong acid, and it's partially because it's such a highly conductive in water, right? And you want that. You want the electricity to flow through your battery very well. Bases also conduct electricity in water. Typically. So both species are good electrolytes, we would say. And if we look at both acids and bases, they have a reputation for being corrosive. So what do I mean by corrosive? Classic example, hydrochloric acid, right? If in every lab we've ever done with hydrochloric acid, I tell you, if you drip this onto your skin, you need to go wash it off very quickly because it will react with your skin and turn it into something, right? If you've ever heard of an acid burn, where you got like vinegar in your eye or something around your hand, it hurts very badly, or an open cut. That's because acid, can do damage to your tissues, or metals, or anything really. And so can bases, right? One of the stronger cleaning solvents underneath your sink, if you go and look, like Drano, is a very strong base, NaOH. And so you can use it if there's a bunch of gunk in your sink. You can pour it down the sink and it will corrode the gunk away and dissolve the gunk or react with the gunk. But if you ever have a sibling, like a young sibling or something, and they accidentally drink it, they're in immense pain. It can do a lot of damage. It could be deadly sometimes. And so you would have to call poison control or something, because it's a very, very nasty chemical for your body, which is also why it's a very good cleaner, right? Generally, cleaners are not good for your body. So those are some bulk properties that we think of when we think of acids and bases. And we're going to talk in more detail about what the chemicals look like so you can understand why they have those properties. So let's look at a molecular definition of what an acid is. And I'm going to take a very easy one. Let's take HCl. If you take a hydrochloric acid molecule, that's a hydrogen attached to a chlorine like so, and let's say you're going to put it into water, big glass of water. So we got a sample of hydrochloric acid. Assume it was it's not a solid like this. I guess you can get hydrogen chloride to be a solid, but you wouldn't. Anyway, let's suppose you could dump hydrogen chloride powder into water. It'd actually be like pumping hydrogen chloride gas into water. What would you see happening at the molecular level? It would look something like this. You would see the hydrogen floating around, attached to the chlorine, and you would see water molecules flowing around, like this. And we believe that what happens is when the hydrogen gets up close to the oxygen, remember oxygen is a very strong element, very electronegative. It actually takes this lone pair of electrons, will bond to that hydrogen, and this bonded pair of electrons between the hydrogen and the chlorine will actually move and stay onto the chlorine. It breaks this bond and it forms a new bond. So I'll draw a little arrow to show that that's how this is happening. And overall what happens in this reaction is you get an oxygen that is now bound to 3 hydrogens. And you get a chloride ion left over. You get this is a positive situation. We actually, we don't take the electron with the hydrogen, so it's just we don't take the negative, so it leaves a positive. We do leave the negative behind. So what happens is, sometimes they call this donating a proton. So to understand that, we have to look at what a hydrogen atom actually looks like. Remember, a hydrogen atom has 1 proton in the middle and 1 electron. If we draw it like a Bohr model floating around the outside or in the electron cloud, that electron was here, right, on that hydrogen, just like it was bonded with that electron from the chlorine. When the hydrogen attaches to the oxygen here, this electron stays with the chlorine. Maybe that's that electron there. But the proton does not, right? That's the only other part of the hydrogen. It stays over here. So this is almost like a naked proton that has just been attached to these 2 electrons on that oxygen atom. And what we end up is with this. So this is a typical acid interaction with water, where a hydrogen from the acid is removed and put onto the water. Let's try another one. Let's try the vinegar reaction that I mentioned earlier. Vinegar is a molecule that looks like this. More or less. And vinegar can react with water in a similar way. Here's a water molecule. When you put vinegar in water, this is the reaction we think happens, which is that this hydrogen, again, a lone pair from this oxygen, comes out and attaches to that hydrogen, but the electron that was bonded here with this oxygen goes and stays with that oxygen. And what this all turns into over here, let's separate this so we're not confused, we would get a leftover vinegar molecule that has lost its hydrogen and now has this oxygen like this, and we would have the water molecule that has picked up an extra hydrogen, just like before. And this, because it kept the electron, would have a negative charge, and this, because it didn't bring the electron with it, would have a positive charge. So this is an acid type of interaction. This is also an acid type of interaction. And the common theme here is that you had something with a hydrogen source, right? It had a hydrogen attached to it. We put it in water, and the hydrogen got taken by the water molecule, but the electron did not. Same thing happened here. The hydrogen got taken, and the electron did not. And what it produced were a couple of ions, the leftover ion here and the water, which has now become something that's not water, right? Water has 2 hydrogens. This now has 3. So let's get some terms here. A general equation would look something like this. Acid plus water. Those are the 2 reactants. Sometimes they write it like this. HA is the acid plus H2O. Because all acids, or at least the 2 that we saw, had hydrogens attached to some other piece. What did it turn into? Well, in the case of the hydrochloric acid, what was left behind was the stuff that was attached to the hydrogen, the chlorine, chloride ion now. The water, it was H2O, turned into 3 H's and an O. So definitely one of the things, and that happened down here too, we got H3O. So one of the products is H3O plus ions. The other product, in this case it was the leftover chloride ion, in this case it was the leftover piece of the vinegar that didn't have the H. So if the acid started as HA, it ends as A minus, right? It had a negative charge at the end, and it was missing the A. It was everything but, sorry, it was missing the H. It was everything but the H. We're going to have a name for that. Actually, let me write it up here. This H3O plus chemical has a name. We call it a hydronium ion. This A minus, if we called the HA the acid, the A minus we called the conjugate base. And you'll get a little bit more of an understanding when I go forward and we start talking about bases, okay? And this is a typical acid interaction. Now, what about bases? So let's take a common base like ammonia. Okay? Ammonia can react with water just like acids can react with water. So ammonia looks like, I should call it ammonia. I said NH4. I'm giving away the game here. It's actually NH3 is ammonia. So NH3 looks like this. And he's got a couple of free electrons in the lone pair. And then we have a water molecule. Let's put a water molecule in there. Now, when ammonia gets bubbled into water, because remember he's a gas, but if he goes into the water and he interacts with the water molecules, we think this is what happens. We think his lone pair reaches out, or this nitrogen kind of snuggles up to that hydrogen and forms a bond using those two, or that lone pair of electrons. And this hydrogen goes, but doesn't take his electron with it. So this electron and this electron stay behind on the oxygen. And what we wind up with is an NH4 molecule like this, only it didn't take the electron with it, so it's actually a positive molecule. This is ammonium. So if you're keeping this together, that's ammonia would be NH3, and this is ammonium with an extra hydrogen. What happened to the water? The water now looks like this. It's lost a hydrogen, but it didn't lose those electrons. They stayed behind. And because they stayed behind, he will now have a negative charge. Okay? That's a standard base reaction. You can see it's kind of the opposite of what happened with the acid. With the acid, the water took a hydrogen. This case, with the base, the ammonia took the hydrogen from the water. So we could say that this is if we're going to say base reactions tend to go like this. They say we start with a base, we add it to water. In this case, the base was, we'll call it B for base, and the water was H2O. And they both react. What did we get? Well, we had the base NH3, but we added an H to it, and it became positive. So it would turn into, let's say, HB positive. What did the water turn into? It turned into OH minus. We have names for these things. If we start with a base and it turns into HB, we call this the conjugate acid. This OH minus, we have a name for that as well. We'll call this a hydroxide ion. So in general, when you add an acid into water, the acid will give away a hydrogen to water, or will give away an H plus to water, a proton to water, forming hydronium and some conjugate base. So the conjugate base is the leftover piece of the acid that lost its hydrogen. When you add a base to water, it will steal a proton from water. It will actually take a proton away, leaving a conjugate acid, which is a base with a H plus attached to it, and a hydroxide ion, which is the leftover piece of the water. Now, these are the kinds of things that acids do and bases do in water, just adding it to plain old water. And you can kind of see, like we started with, we said that both of them are good conductors of electricity in water. Well, here's why. Once you put it in water, in both cases, you get a positive and negative species, which, remember, ions conduct electricity in water, and same thing happens with the acid. So that's why they tend to be conductive. Now, what happens if we eliminate the water from the equation? Well, I could take HCl. Let's take hydrochloric acid, and let's react it with a NH3. When I react hydrochloric acid with ammonia directly, this was the acid before, this was the base before. Let's see what they would do. In this case, I'll draw it out. We have an NH3, and the NH3 is a strong guy who can take hydrogens. We have an HCl, which was apparently a fairly weak interaction, right? Because it was easy for water to steal the H from the hydrogen chloride or from the hydrochloric acid. It was easy for the NH3 to steal an H from water, so by that token, it should be very easy for an NH3 to steal an H from hydrochloric acid, and that's exactly what happens. So the NH3 reaches out, grabs onto that hydrogen, takes the hydrogen but leaves the electrons behind. They stick there. And so what's left at the end, we're going to get this NH4, and it will be positive. And we'll get that chlorine, that chloride, and that will be negative. So this HCl plus NH3 would turn into NH4 plus and Cl minus. Now, I'm drawing them separate. As we can see from this, a negative and a positive would probably stick together. This would probably be an ionic compound, ammonium chloride. Let's talk about this nomenclature. We said this was the acid and this was the base. This was the HA. Over here, look at this. We have an A minus, right? This is like HA, and this is like A minus. Up here, that meant that if this was the acid, then this A minus is the conjugate base. So chloride is the conjugate base of hydrochloric acid. And ammonium, by the same token, right, if we had B that turns into B or HB plus, which this did, it was NH3, we added an H plus to it, this would be the conjugate acid of NH3. So we don't need water to form a conjugate acid. We could just do it from another acid-base interaction. Okay. This is sometimes called a neutralization reaction. One of the reasons that, for instance, a base might be very caustic to your skin is your skin is full of carbon-hydrogen bonds, and so a strong base could come in and pull some of the hydrogens off, which would change your skin into something that wasn't skin, which would do damage, right? So having a base around would be very harsh. Same thing with HCl. HCl can react with your skin in the opposite way and donate its hydrogen, etc. And again, turn your skin into something that's not skin. That would be bad. But if you took an HCl and reacted it with an NH3, what you get is neither an acid nor a base. You get basically an ionic salt. So together, NH4 plus Cl would be NH4Cl. That's a salt. A salt is the combination of the positive and negative ions that you get when you react an acid and a base together. And salts are not always dangerous to you, right? So acid and base coming together, typically called a neutralization reaction, in which a salt is typically produced. All right. Let's do one more thing we're going to talk about, which is about relative strengths of acids and bases. So there are let's take the HCl that I used earlier. If I were to take like 100 grams of HCl and dump it into a liter of water, okay, in it goes. It will mix around. It will form those H3O pluses and the Cl minuses. We know that it's going to be HCl plus H2O goes to H3O plus Cl minus. Okay, that would be what's happening inside the solution. Now, I'll tell you from experience, when I dump HCl in there, all of it reacts completely. Okay? There is no equilibrium state where this goes backward. I mean, there might be a slight backwards thing, but it's so small as to be immeasurable. Effectively, this goes one way and it doesn't go backwards. Okay? So once it's in there, if I were looking around, I would not find any HCl molecules. I would only find H3O pluses and Cl minuses. It completely reacts. Okay? Let's suppose that I do the same reaction, but instead of using HCl, I use the vinegar that I talked about earlier, I'll just write the formula for vinegar, CH3COOH. And I put that in water. And it reacts like this, CH3COOH plus water turns into CH3COO minus and H3O plus. Now this, unlike the hydrochloric acid reaction, the forward reaction for this does happen, but the backward reaction happens as well. In other words, whenever these guys are floating around in solution, occasionally they'll bump together and the hydrogen will go back and they'll return to products, just like we talked about in the equilibrium chapter. And that happens in significant amounts. These reaction rates are close enough that I would have some of each. I would have CH3COO minus, I would have some H3O plus, but I would also have some original vinegar molecules, CH3COOH in there. At the same time, it's not like this that goes only one way. And when they go backwards like this and not all of the acid reacts, we say that's a weak acid. When they only go one direction and it completely dissociates, we would say that's a strong acid. Okay? And what they're effectively talking about is how strong, who holds onto the hydrogen more strongly. In this case, water is so much more strong at holding onto that hydrogen than the chloride ion is, that if it doesn't go backwards. Once the water takes it, it's stuck to the water. Here, this is called an acetate ion. This acetate ion can actually pull a hydrogen off of water with a certain amount of regularity, and so we would say this is a weak acid. It doesn't give away its hydrogen as easily as this hydrochloric acid does. So in terms of strong versus weak acids, the one who's stronger gives away the hydrogen more easily. Okay? What about bases? Well, you could talk about the same thing. Ammonia, the one I mentioned earlier, NH4 or NH3, is actually considered a weak base. So when ammonia reacts with water, NH3 plus H2O turns into NH4 plus OH minus. Okay, that forward reaction happens with a certain regularity, but the backward reaction is significant, and so this stuff will get back together. The hydroxide will steal a hydrogen back, and you would get an equilibrium set up between the products and the reactants. So this would be a weak base. A strong base would dissociate completely in water. Something like sodium hydroxide is considered a strong base. So when you put sodium hydroxide in water, and you get effectively OH minus and Na plus effectively. That basically doesn't go backwards. It's a one direction. So this would be a strong base. And we'll get into pH and things like that in a future video. So there you have it.